What's up, everybody? Isaac here with Civil Engineering Academy, coming at you with another podcast episode and YouTube video. So if you're joining me on either one of those platforms, I thank you very much. Hey, while you're at it, if you are listening to the podcast, feel free to jump on and go give us a sweet review if you can do that. That would be much appreciated. And if you're watching us on YouTube, give us a thumbs up too. Those things kind of help us out. Anyway, I hope you guys are doing well. In today's episode, I want to detail a lot of questions that we typically get around the topic of seismic course material. So in California, you have to take an additional exam even after you take the PE exam that details taking an exam on seismic and as well as survey topics. So you have this additional information that you need to have for those that take that want to earn their PE license in California. Now, this topic also applies to specific depth reviews, specifically the Geotech. As you dive into the spec there, you'll see that there is a lot of seismic material there. And to be frank, the Civil Engineering Reference Manual that most people have, if you don't have it, go get it. It's at civilengineeringacademy.com/PPI, and you can use our discount code of CIVAC to get 15% off to get that. But for most people that get the CERM, and I've got a copy over here, it's very thick, but it does not include a lot of material on seismic for whatever reason. It needs to be updated to include that material. So what I did is occasionally, as part of our courses, we have the civilpereviewcourse.com, we have our FE review course at civilFEreviewcourse.com, and we have depth review courses that you can go check out at civilengineeringacademy.com. But occasionally we do live problem-solving workshops. Recently I did one, I believe it was last Saturday. We are sitting in April. The PE exam is coming up very soon. I wanted to do a live problem-solving workshop. And what I thought would be fun today to do is just put on the podcast and also make this a kind of a permanent video out on YouTube and our other social channels about our live problem-solving workshop. So you can see how we do it, the look and feel. Also, maybe it might be a good review for you as we detail some of the topics that we cover, including seismic waves, talking about surface waves, body waves, and a couple questions regarding those. We also talk about liquefaction, and along with liquefaction is some terms that we detail that we call CSR and CRR values, and we talk about that in the workshop. We also go over seismic base shear, which is coming out of the ASCE code, and make sure you understand how to solve that. We talk about deep foundations a little bit, and some also deep foundation theory questions. So those were the range of topics that we covered while we were discussing the live problem-solving workshop. My goal with this is just to kind of give you either an auditory experience of that workshop, or if you're on YouTube, you can watch it, see how we do that, but also let you know that we are in the works of developing our own seismic review course at California Seismic Reviewcourse.com. It's going to be on our main website as well at civilengineeringacademy.com. If you want to be an early adopter of that, or if you are in the market to pass your exam in California and become a licensed PE, my brother Mark is really diving deep into this course, and it's really been a fun project. We're excited to share it with the world very soon as Mark works on that. So if you would like to take part of that and be part of a kind of a beta release, a beta program, then you should definitely check it out. Sign up on any of our newsletters. Go to civilengineeringacademy.com or go to California Seismic Reviewcourse.com, and you can be an early adopter there. All right, guys, with that, we're going to go ahead and jump into the live workshop. And if you have any questions about any of this, feel free to email me, Isaac at civilengineeringacademy.com, or you can email my brother Mark at civilengineeringacademy.com. We're just excited to share that with you, so go check it out. And it's going to be coming right up. Sorry for the very long intro, but you got a lot to say, and this one's going to be a long one because it was a long live workshop. It's a little bit out of the norm of what we do, but I thought it'd be fun to share. So check it out. Let me know what you think. We'll see you in there. Bye. Hey, what's going on, everybody? Isaac here with Mark. What's going on, Mark?
Hey, I'm just enjoying the opportunity to join you again, Isaac. It's gonna be
Nice. So today I'm running the show. So you guys are in for a treat. We're going live today. Today we're going to hit some topics detailing seismic material as well as some deep foundations. It's kind of all over the place, and really this is a depth topic that you're going to find for geotech, not necessarily, general stuff or broad stuff for everybody, for all topics. So if you are in need of something this specific, or you need other specific material covered, feel free to email us. You can email me, Isaac at Civil Engineering Academy. But we also have a depth course. You can go check that out, and it should cover all these topics for you if you are needing a quick, dive into your own particular areas. So you can go check that out at civilengineeringacademy.com if you'd like. So anyway, with that, I say we get going. What do you say?
Let's roll, baby. Yep.
All right. So I'm going to add this to the stream. We're going to go straight to a big board, and we'll maximize this. All right. So the first thing we want to do is review some seismic waves. Very common questions that come up just as part of our seismic review on this. And I'm going to get rid of this banner. If you need a course, go to civilengineeringacademy.com. All right. So first thing we want to do is review seismic waves. And one of the things we get asked quite a bit is kind of the difference between these. So, this is a lot of seismic stuff that comes up specifically on the geotech depth can be theory. So that's kind of why we hit it a lot. But all right, quick review. When an earthquake hits, you have two types of waves hitting. So for those in the audience joining us, if you're studying seismic material, what do you know what kind of waves are hitting? What are the two type of waves that are hitting when we have an earthquake? Anybody? We'll wait for just a second. Let's look at the comments. We're doing great work. Well, thank you.
I know.
For us.
See that? I
appreciate that.
Yeah, I always appreciate that.
All right. I don't know if anybody knows, but if you do know, leave a comment in the chat room and we will definitely check it out. So when an earthquake hits, you have two different types of waves hitting. And so what are they? They are called body waves and surface waves. And within that, I kind of gave a hint here, but within the body waves, there's two different types of waves as well. And Morgan got it. You got P waves. You got P waves, you got S waves. So if you do any research online whatsoever, you're probably going to come across some videos. This is a goofy one I found. No offense to any professor that might be watching this.
What if somebody online's actually in the video?
I don't know. But, you do any sort of research online and you can get a good feel of what a P wave and what an S wave is. You can also get a good feel of what a surface wave is. And so, I just threw this in here because I thought it was, a fun video showing some humans. Let's see if I can, hopefully you guys can see this. So here's your example of your P wave. P wave stands for pressure wave. So the guy jumps, hits a guy. These guys are acting like molecules. But basically, when you have a P wave, these are called primary waves or compression waves. So if I can write this down, let's see. P waves are primary waves. Or they're sometimes called compression waves. And they, just like this example showed, a guy hits them and they just kind of move back and forth. Kind of like a slinky if you were just to give it a kind of a push. It just move back and forth. An S wave, slightly different. I don't know if there's a good example this guy does. I think it's right here. I won't show the whole thing. But basically he has them interlock their arms and he shakes one of them and they kind of shake like a snake. So an S wave, if you think of a slinky, it's kind of doing that S. It's kind of making that S snake move. So you've got your S waves. They officially are called secondary waves. or they're called shear waves. Okay? So those are the two different waves that you have within a body wave. So again, you've got an earthquake hits, you're going to be hitting two different kinds of waves. One set are called body waves, the other are called surface waves. Hopefully that makes sense to you. Within the surface waves, you have two different kinds. One's mainly called the Raleigh waves, and the other one's called the Love wave. So these are named after the professors that discover these. There's not some hidden meaning here on the Love wave there. So for surface waves, we deal with Raleigh and Love waves. Raleigh causes some rolling and heaving as the wave moves, and Love waves deal with sideways movement. So a common question that they might ask you on an exam is something to do with this. What causes the most destruction to buildings? Is it going to be P waves? Is it going to be S waves? Are they going to be Raleigh waves or Love waves? Does anybody know? Michael Coleman seems to be on it. He's got P and S waves listed, P waves. Does anybody, if you could take a stab at problem one, what causes the most destruction to buildings? Good question. And really, guys, to really dive into these topics, you either need a good depth, a good geotech book that you can dive into that's going to detail some of this, or like Goswami, you need a book where it details some other stuff like Goswami. He dives into a little more detail on the depth sections versus it's CERM. CERM doesn't hit really seismic material, which is a big fault that they need to update on. So we got some questions. We got some answers coming in. Let's highlight some of these.
Yeah, we got some answers, Isaac.
Kevin Morgan, Raleigh, because it includes both P and S. One guy on Facebook said P waves. And I think, Kevin, you are correct. So Raleigh waves are produced with P and S waves. They involve both vertical and horizontal particle motion. It can cause quite some damage. Love waves do as well, obviously. But from everything that I have read and experienced, the Raleigh waves are surface waves, and they produce ground motion in both vertical and horizontal directions. And you basically can have buildings, rolling, so they're being lifted up and they're dropping to the ground.
Hey, Isaac.
Yeah.
Just a way to visualize a Raleigh wave is maybe like the surface of a lake or an ocean where there's not really, things going on underneath. If you were to draw a picture of Raleigh wave, maybe draw like the surface of the ocean with some undulating waves. Those waves are acting at the surface.
You got some waves up top.
Yeah, but down below, there's really not much going on. So those Raleigh wave, there you go. That's a perfect Raleigh wave illustration.
So yeah, these are your surface waves. If this is the ocean, this is what you're dealing with on the surface. The P and S waves are bouncing around underneath the surface, and they can bounce off the surfaces, they can refract, they can change direction, they can reach to the top, they can do all kinds of weird stuff. They can just go straight through. So these guys are the Raleigh and the Love, and these guys are like the P and the S. Okay? So, this is a good theory type question, but it also tests, this is basically starting comprehension of seismic waves and seismic material. Is there any questions surrounding this from anybody?
I'm not seeing any questions pop up, Isaac. It looks like you're nailing it.
Anyone getting on the love train? All right. Cheesy dad jokes. All right, let's go to problem 2. All right, problem 2 we're going to talk about real quickly is liquefaction. So a quick review of that is that liquefaction occurs when saturated sands break down rapidly due to an applied load, like an earthquake. As the shaking continues, the loosely packed soil attempts to move closer. There's not enough time for the water to escape, so the water ends up being confined and the soil doesn't get closer. So to make this happen, you basically need 3 things to occur. You need a saturated soil. So this means you got water. Okay? You need rapid loading. You need an earthquake. And 3, you need soils that are susceptible to this. Basically, a sand. So something round, clean, uniform, has a low effective stress, low density. We're talking about basically sands here for this. So again, this is a topic that can range in a lot of different areas, but really I just wanted to hit some conceptual stuff here with you on this, and we'll dive into other topics here shortly. So problem 2, I wrote here, which combination will most likely lead to liquefaction during a high magnitude earthquake? So giving that quick little review, we got to use some engineering judgment here. And if you're in the audience, you can participate if you would like. So let's look at it. A, ground made up of multiple layers with a large amount of groundwater. B, sand with no groundwater. C, soil strata made up of multiple soil layers with little groundwater. Or D, ground made up of rock with little groundwater. So let's just go through these a little bit. A, if you have a ground made up of multiple layers, you have a good chance one of those layers is sand. And if you have a large amount of groundwater, then that's definitely a choice we want to select. B, sand with no groundwater. If you have no groundwater, you're not going to have liquefaction. You need to have a groundwater, right? Some sort of water involved here. Saturated soils. Kevin's got it. And let's see, Jessica got it. Excellent.
Yeah, it looks like most people are honing in on the right answer, Isaac.
You got it. So C, soil strata made up of multiple layers with little groundwater. That's, you'd have no groundwater again. And then D, ground made up of rock with little groundwater. Again, no groundwater, and you're dealing with rock. So rock's a good thing. You're not going to have liquefaction. With the rock, it's not low density. So good job, guys. The answer here is A for sure. That's your best choice. You have a best option of hitting sand, and you're dealing with water. Let's just look at this one, problem 2A. It's been determined that a proposed construction site is on a liquefaction susceptible location. Which statement is true about this location? Do you want to avoid construction here? Do you want to improve the soil strength, drainage, and density? Which one of these is true? True. Improve the soil strength, drainage, and density. Do we want to design the foundation to resist the effects of any liquefaction, or do we want to do D, all the above? Any thoughts on that one? If we go through each one of these, we could straight up, we're getting some answers here.
Yeah, we've got an answer B.
B is a good answer. Improve the soil strength, drainage, and density. And D is also a good answer. So now the secret here is this is the kind of crap they might throw at you on the PE where you're going to have good answers. So you have to really think about it. In this case, you could straight up avoid construction here. That is an answer that is acceptable. If you found liquefaction in an area, you could avoid it. B, it's not, it's probably not ideal if you have to build there, but if you could avoid it, you could. That's a true statement. B, improve the soil strength, drainage, and density. Yes, we could do that. There's lots of methods that you could use to improve the soil, the drainage, and the density to try to remove liquefaction potential. C, design the foundation to resist the effects of liquefaction is also a possibility. You could go deep. You could build to a rock layer. get a deep foundation going. So the answer here really is D, all the above. Okay. And so these are the kind of questions that you could potentially see on the PE exam, where you have lots of good options, and you just need to think through every option here and make the best selection. So you guys definitely were catching on there. Good job, everybody. Any questions just loosely regarding liquefaction before we dive into something here a little deeper with liquefaction? Probably not yet.
Yeah, I'm not seeing any questions here. I think you nailed this one again, Isaac. Good job.
Oh, I like that. I keep nailing these things.
You're nailing it.
If I screw up, I'm sure the audience will let me know quickly. All right, let's dive into something a little more juicy here. Problem number 3. So we want to do another quick review of what CSR and CRR are. Wow, that's a lot of R's. To evaluate liquefaction potential, you can use 2 methods to evaluate. One of them is called the CSR and the other one's called the CRR, which stands for cyclic stress ratio and cyclic resistance ratio. So what CRR means is it represents the capacity of the soil to resist liquefaction. That's simply what it is. And CSR represents the seismic demand on the soil and is a ratio of the horizontal shear stress to the vertical effective stress. Pretty straightforward. This could be likened, I believe we said, to a Poisson's ratio.
Yes, the CSR could be likened to the Poisson's ratio.
The Poisson's ratio. So I can't even spell Poisson. Poisson ratio. So very similar to that. So if we look at an equation, I'm going to show you the equations as we solve these problems. But if you are diving into these topics, my hope is that you have a reference or some sort of material that you can reference to determine these equations. Okay. But we'll go through this anyway. So problem number 3. Groundwater for a site was 12 feet at the time of the testing. The average horizontal shear stress was 500 pounds per square foot. Based on corrected blow counts, the CRR was determined to be 0.4, which also includes the correction for a 7.5 magnitude earthquake, which is a severe earthquake, right? That's a doozy.
Yeah, and I think that's the benchmark. Well, it's not the benchmark, but it is classified as a severe one for sure.
Yeah. So the question here is, what is the factor of safety against liquefaction for the sand below the water table, given the density is 115 pounds per cubic foot and the saturated density is 118 pounds per cubic foot? So we got a little diagram here. You've got sand going down. You've got water table down here at 12 feet. You've got a clay layer down here at the bottom. So what we could do is, the first thing that we need to do is determine the vertical effective stress at the midpoint of the saturated sand layer, which is going to be right here. Boink. So first thing we're going to do is solve for that. So what's effective stress? We have to take that first layer, which was determined as 115 pounds per cubic foot. And I'm not going to write down all the units here. We're going to multiply that by the thickness here of 12 feet. That's the layer that we're dealing with. Now we have to add the next layer here was 118 pounds per cubic foot. And we're going to subtract out the pore water pressure, which is 62.4 pounds per cubic foot, and multiply that by 4, which gets you down to halfway point of that sand layer. Is everybody clear on how to solve for effective stress? Hopefully so. That's if you're in the geotech world and you're studying for this exam, you should know how to solve for the effective stress at a certain level down there. All right, so if I punch that out, I get an answer of 1602.4 pounds per square foot. So that gives you your vertical effective stress at the midpoint of the sand layer. The next thing we have to do is calculate the cyclic stress ratio, which is CSR. And the equation for that is this. We said it was a ratio, right? Up here, it's a ratio of the horizontal shear stress to the vertical. So there you go. So we've got a ratio of the horizontal shear stress to the vertical shear stress, or effective stress, sorry. And that's your equation for CSR. We were given what the horizontal shear stress was. And in all honesty, I'd probably write down what each of these values were right over on the side, just so it's a quicker reference for me, you know. Horizontal shear stress was given to me as this. CRR was given to me as 0.4, but it says this also includes a correction for 7.5 magnitudes, so that's for a CRR of 7.5 magnitude. We're solving for the factor of safety, and you were given these. You could write in the layers if you wanted to. So this is pretty straightforward. This was given as 500. And you're going to divide that by what we just solved for, 1602.4. And I get an answer here of 0.312 is my ratio. Okay, now that we got that, we can solve for our factor of safety. There is an equation that lists to solve for the factor of safety is equal to your CRR of 7.5. And you divide that by the CSR, and that gives you your factor of safety against liquefaction. So if you simply just solve that out, your CRR of 7.55 was given as 0.4, and divide that by the CSR we solved for, 0.312. If my math is right, I get an answer of 1.28. Boop. So these are the equations that you're going to need to know if you're solving for CRR and CSR. Which will help you out. And so like I said earlier, you need to have a good reference, a good book, a Geotech Depth book, use Goswami's reference material to really hit some of the seismic material, or a good Geotech book so that you can solve these type of equations and problems that come up. So,
well, Isaac,
any comments, Mark?
It looks like you're nailing it again. I'm not seeing any questions there, but this is a good one. I like how we've related your CSR to Poisson's ratio. And it's kind of cool to see that the factor of safety is really just a gauge. It's a measurement on when the horizontal stress, or excuse me, when that vertical stress exceeds that horizontal stress and everything starts moving and you get that liquefaction.
So if your factor of safety is 1.28, you're saying basically you're 28%, you're able to resist your liquefaction by this amount.
Yeah, it's like any factor of safety, right? Your overstrength or your factors of safety, you're almost 30% greater than the capacity that you need to resist your stress.
Which is good. So maybe you did something to the soil, you improved it in some way, maybe you were shooting for a factor of safety of that, or maybe you need more. Maybe you need a higher factor of safety and you need to improve the soils.
Yep.
So that helps you determine that.
It's a good one. You nailed it, Isaac. Good job.
All right. Any questions? Doesn't look like we have any. If you do, leave them in the comments. We can always come back to some of these problems. I'm going to march forward because we got some doozies in here. All right. Problem number 4. This is a good one. So now we're going to start diving into the code. So as part of this review of seismic material, I wanted to cover seismic base shear. And according to the ASC 710, which is what's used on the exam right now, they haven't upgraded. I believe they have a 716 out now and probably a new one shortly after. But
Yeah, 7 ACI, or excuse me, ASC 722 is going to get released here fairly soon.
Yeah, so it seems like everybody lags behind on when they're actually released versus when they're adopted, and it sounds like the NCES just hasn't gotten around to
it's all good.
updating that. So hold your questions on the standards. We're sticking with 710. According to 710, ASC 710, the seismic base shear, what am I trying to say? Using the equivalent lateral force procedure in a given direction is determined by this equation, V equals CSWS. And so what we want to do is quickly review the ASC 710, which kind of gives you the whole breakdown of how to solve for this, this type of equation. And then we'll do a quick problem. So seismic base shear, just like I said, is given by this equation, this 12.8-1, where V equals CS times W. CS is the seismic response coefficient. So if you likened, what we're trying to solve here to F equals MA, we're finding a force that's hitting the building that's happening on that very ground level, and you're taking some sort of earthquake information that we're going to plug into the CS value, and we're going to multiply it by W, which is basically the weight of that building, the effective seismic weight. And sometimes, when you're solving these things, like California, we're in Utah, we have high seismic loads here in Utah. Sometimes these values for CS, that you're multiplying by the weight of the building can get quite high, almost two times the weight of the building. If you took like a 10-story building and you can imagine how much that weighs, and then you're multiplying that by 2, that's a lot.
Yeah, Isaac, you can attribute that, or you can equate that equation to Newton's, good old F equals MA equation, right? So you can have a given mass, which kind of relates to your W, but the higher the acceleration, right, the bigger the force, or the bigger that V, the bigger the shear is going to be. So
yeah,
you can think of it that way as well.
Good deal. So as part of that, like I said, we have to find out what the CS value is, and it kind of just runs you through a lot of equations that you will need to find some variables for. So if you jump to 12.8-2, you have to find what that CS value is, which is the seismic response coefficient, and that you can see here that it's equal to SDS divided by R over I. R is equal to, SDS is the design spectral response acceleration parameter in the short period range as determined by these equations, 11.4.4 or 11.4.7. And so that's why we've included some of those sections kind of over here as you start diving into what you really need to solve this. R is the response modification factor pulled from a table. IE is the importance factor determined in accordance with this section 11.5.1. And they can't exceed the values of CS computed. You have to follow these rules as part of this code. So your short period T has to be less than TL for this equation, 12.8-3. If T is greater than TL, then you got to use 12.8.4. And it can't be less than this guy, 12.8-5, where CS is equal to this fun equation.
And Isaac, it's worth noting that seldom does that equation 12.8-5 apply. It's very rare that happens.
Okay, good to know. So, as diving into this, you got to find what SDS is. So if you're going to go find what SDS is, we're going to section 11.4, and you'll see that SDS is equal to these guys. So it's SDS is equal to 2/3 SMS. And then you got to go find out what SMS is, which leads you to this section over here. And I've kind of just copied and pasted a lot of this for you guys to look real quickly, but you would have to thumb through this, and hopefully you've got this tabbed up pretty well for your own exam. So you're not thumbing through things like crazy, or you've practiced enough problems that you just know what you need, is really the ideal situation. So, okay, so eventually you drill down to what SMS is, which was titled here, Site Coefficients and Risk Targeted Maximum Considered Earthquake Spectral Response Acceleration Parameters. The MCE, Spectral Response Acceleration Parameter for short periods, which is what SMS is, and 1 second periods, so SM1, adjusted for specific site class effects, shall be determined by these equations. So this stuff is pulled from maps and data. You've got seismologists that are out there pulling, they've got measured locations on maps, and you can pull this information from those locations. So SS is listed here. So if you look at what SMS equals, it's equal to FA times SS, and SM1 is equal to FV times S1. So SS is the mapped MCE, spectral response acceleration parameter at short periods as determined in accordance with this section 11.4.1. And S1 is the mapped MCE, spectral response acceleration parameter at a period for 1 second as determined in accordance with 11.4.1. Where site coefficients FA and FV are defined in tables. Mark, you brought up some good comments about this in some of your studies before. What did you say on that?
Yeah, just that those mapped accelerations are always expressed in terms of percent of gravity, percent of the acceleration of gravity. And like you were talking about, there's two separate maps, both, one for the long period and one for the short period. One for the long period is the 1 second period, and the short period is the S sub S value. You need to make sure you're looking at the right maps as you're kind of thumbing through your ASE 7. But they're just they're spectral response values that are derived or determined from seismologists that have actually gone out there and hooked up a seismometer and measured percentage of gravity accelerations for given events, given seismic events. And so they think they got a pretty good beat on how much acceleration is going to happen in a given area based on those maps.
Okay, good. So I just pulled up here what FA is. Like we said, it comes from tables. So in table.11.4-1, we have the site coefficient FA. So you just look at what site class you've been determined where you're building. So if you've been given a certain site class, which is dependent on soil conditions and such, you can go look up what your value should be. And you've been given these different values for what SS is, which is based on what comes from the map, right? So you go find an S, let's say you're in class D, and you've got an SS of 1.0. So if you're class D, you, if I'm reading that straight across, it should be 1.1. And then lastly, I don't know if I hit this, but you've got this design spectral acceleration parameters of SDS and SD1 for the short term and the 1 second duration. And those are the equations for those. So my point in showing you all of this is that you take a simple equation, V equals CS times W, and you realize that there are a lot of different pieces that you may need to solve for this equation. And the truth of the matter is that on the PE exam, any one of these pieces could be, a question, a piece of the puzzle that you may need to encounter. So when you're practicing and you need to solve for a seismic base shear type question, it's good to pay attention to all the steps that you need to see in order to solve that, because any one of those other steps could be a potential question that you might get hit with. So I guess before we, carry on, any questions on the code that I'm diving into for seismic base shear? If there is, leave them in the comments and we will get to them. So let's get to an actual question that we might have to solve for this. So here we go. Problem 4, a 12-story building listed on a site class D. This is all good information. So, I mean, you could be jotting this down, right? 12-story, class D, has a response modification factor, R equals 5.6, and a seismic weight, W, is equal to 3,000 kips. Sorry for the handwriting. The mapped acceleration parameters SS, so they got this from a map, 1.25, and S1 is equal to 0.45. The seismic importance factor, so that's IE, is equal to 1. Is that, can you guys read this? I don't know if you can. That's a 4 and a 5. Let's redo that.
Yeah, I can read it.
Can you read that? Okay.
Yeah.
All right, the fundamental period T, so T is our fundamental period, and that was given as 2 seconds. And the long period, TL, is equal to 3 seconds. What is most nearly the seismic base shear for the structure? So as soon as you say seismic base shear, what's the equation we want to use? V equals CS times W. So the first thing I need to look up, we know what W is. Boop. We don't know what CS is, and now we got to go through all those steps. So first thing we need to do is we're going to write out what CS is. CS is equal to SD1 divided by T times R over IE. That comes right from the code that we just reviewed. And I could show you again up here. Okay, 12.8-3. And that is specifically for T less than or equal to TL. So T here is less than or equal to TL. That's why we're using this, right? All right. So next thing we need to find here, we don't know what SD1 is, so we got to solve for what SD1 is. And if we go back up to our code, SD1 is 2/3 of S1. 2/3 S1, which equals 2/3 times 0.45, which equals 0.3. This is your 1 second spectral response. So now we can say that CS is equal to 0.3 divided by 2 times, 2 was given as T, right? Plugged in 2. And R was given as 5.6. Divide that by 1. And that equals 0.027. So there's your seismic response coefficient. So there's some other parts to this. We can't just assume that's all we need here. We have to calculate now the minimum CS. Make sure we're all kosher and valid here. So next thing we need to do is calculate the minimum. That equation was given up here as CS is equal to 0.044 times SDS. That's a D. Times IE, and that has to be greater or equal to 0.01. So now we have to find what SDS is. To find SDS, you have to solve for SMS, which is, so SDS is the short period. To solve for that, we have to find the max period, which is what SMS is. And we use equation 11.4-1 and the table that we showed. So if you go up there and look at it, SMS is equal to FA times SS. And from FA, to solve for FA, our SS was given here as 1.25. And if you go up and look at the table for 1.25 for the site class D, 1.25, you can see that it's 1.0. Okay, hopefully you can see this up here. 1.0. So if you're going to solve for SMS, your FA is 1 and your SS is 1.25. Mark, am I missing anything? You checking me?
No, you're doing great.
All right, let's keep going. So the max considered spectral response is from equation 11.4-3, and that says that SDS is equal to 2/3 SMS, which equals 2/3 times 1.25, which equals 0.833. So what's the minimum coefficient? So the min coefficient, seismic coefficient. So now we can plug it in here. So CS is equal to 0.044 times 0.833 times 1. And that has to be greater or equal to 0.01. If I work that out, I get an answer here equal to 0.037, which is okay. So therefore, you're going to use 0.037. Okay? So now we go back up and we say, okay, our seismic base shear, V equals CS times W. Now we plug in our 0.037, and we're going to multiply that by our 3,000 kips, which was given to us, and that gives me 111 kips. That's a lot of kippage. So that, my friends, is a quick rundown of using the ASCE 10 code, solving for seismic base shear, and seeing how that works. Now, you're getting a seismic base shear at the bottom. Another class, a deeper dive would be that you could solve for this as it applies to other levels of the building, right?
Well, yeah. So we can say, Isaac, that base shear is kind of a reaction to all the shears that are being imposed on every story going up through that building, right? So you could divide that base shear up just using statics. If as thinking of the concepts that we're looking at here, that base shear is kind of the main reaction to all the shears that are getting distributed throughout the stories on that building because of the seismic event that's occurring.
Good.
So if you were to draw a big arrow at the bottom of that building that you've got there, and label that V, then you could draw little arrows on every story going up the building, and they'd be in the other direction, Isaac, right? Because they'd be reaction to there you go. So all those little V's that are being imposed at every story, all those add up to the big V, which is the base shear.
The big V.
That's the big V.
So, hopefully this whole problem just gives you a new respect if you aren't studying this yet, of knowing what seismic base shear is, how it works, using the code to solve that. You need to be familiar with that as part of this, the ASCE 710. Probably spend a lot of time on that.
And it's worth mentioning too, Isaac, this problem is a little kind to us, and in the fact that it just gives us the importance factor. It just gives us the fundamental period. It just gives us the response modification factor. All those items are, that's a whole nother subject for calculation that you'd have to get into.
Do you have any questions on this one?
Looks like we've got one here, Isaac. It says, and what do you do if your CS min is not greater than or equal to 0.01? Or do you use the other C sub S solved for? Or does it mean we did it wrong? It happens so infrequently that I would worry about having done something wrong, is the short answer on that.
Okay. it's good to know.
So in a test situation, if you're finding out that is the minimum, then I would go back and look at my calcs because you're probably doing something wrong.
Good question. All right. Any others? We will move to the next one here. I know we try to keep these to an hour, and dang it, this topic and the other ones are just long topics. So, all right, quick review of this. Let's go through it real quick. Piles. We're going to do deep foundations now. So piles, they're slender foundations driven or drilled into the ground. They can be steel timber. They can be steel casing, which is just a big steel kind of thick ring with reinforced concrete. They can be you have friction piles. They get their load bearing capacity from the friction from the soil along the pile shaft. You have end bearing piles. They get their bearing capacity from the soil layer below the pile and transfers the load to the rock or a hard layer at the very bottom. When are they used? They're used when shear strength of upper soil is insufficient or too weak to support the load. So if you have crappy soil on the top and you got to get deep. They're used when you have expansive soils or collapsible soils or really compressible soils that are present. They're used when foundation soils have scouring effects. So if you're thinking of building across a river or something where you've got moving water, you're probably going to want a deep foundation. They're used to resist horizontal forces and support vertical loads. They also resist lateral and uplift forces in structures like transmission towers or offshore platforms. I have used these a lot in my own industry for some transmission structures, and they can get very large when you start modeling these things. So like I said here, get a good geotech textbook for these kinds of problems that come up. You know, you could also be dealing with group piles, skin friction, installation methods. Those are usually theory questions. Pile dynamics, testing, integrity test. These are all topics that come up. Today, we're just going to hit capacity using skin friction. You want to check out the CERM Chapter 18 for this. There are several different ways of calculating skin resistance of pile and clays. One of the methods is called the alpha method, and it's a very common method to solve. There's also methods called the beta and lambda methods. I'm not covering those, but the alpha method calculates skin friction as a function of the cohesion of the soil. So let's go through this.
You said CERM Chapter 18, but I think you meant CERM Chapter 38.
Yeah, I think I wrote it right and said it wrong.
Okay.
38. Sorry about that. All right, so let's look at this question. A 2-foot diameter pile, so we've got 2-foot diameter, is driven 50 feet into the ground. That's going to be our length. This is diameter. Into a normally consolidated clay. That's good to know. The soil strength varies linearly from 0 at the surface. So if we have this thing drawn out, it's 0 at the surface down to 1200 PSF at the pile tip. The estimated adhesion factor is 0.8. So that's what this symbol is the adhesion factor, alpha. What is the total capacity of the pile? So if you go to Chapter 38 and you read up on piles, you'll find that our total capacity, Q, is equal to the QS plus QP, or the skin plus the tip pile capacity. And you will also see that QS is equal to the summation, if you had multiple layers of alpha, times SU, which is our undrained shear strength, times your delta L, or length, times the perimeter. So here we go. We've got some variables. We can start looking at what we need to do here. To solve for SU, what did we get here? The soil strength, which is our undrained shear strength. We could write that here. SU is equals to 1200 PSF. In the case of the equation, though, we want to find the average soil strength. So to solve for SU, we take 1200 plus 0 at the top, divide it by 2, and you get 600 PSF. That is the average soil strength on this pile.
So we understand that because in the problem it says that it varies linearly from 0 down to 1200. Okay.
It varies linearly, which is why I tried to draw this out like that. We know the length is given to us. We need to solve for perimeter. P is equal to pi times d. So that's equal to 3.14 basically times 2. So something like 6.28. And now you can solve for what QS is. QS is equal to 0.8 multiplied by 600 times 50 times 6.28. And that equals 150,720. Or, I'm going to just round it, about 151 kips. Okay? Are we cool there? Everybody, did I put you to sleep yet? Wake up, Kevin.
I'm not seeing any questions, Isaac, so you must be nailing it.
All right. Well, now that we've solved for QS, I'm going to scroll this down a little bit more. Whoops. All right. Now we need to solve for the tip. So QP is equal to, and these are equations in the SERM, but QP is equal to NC AP times C. Now, NC is equal to always 9 for these kind of problems, and that's because it's coming from the Terzaghi cohesion factors. You can look that up. Table 36.2 in the SERM. If you remember, solving for bearing capacity, there's these factors. Well, if you're dealing with driven piles, this is typically always 9 for driven piles. And then we've got area AP, which is the area of the pile tip. And we can just solve that right here if we wanted to. Pi fourths d squared. So pi fourths times diameter was 2 feet. So that cancels out. You got 3.14 feet squared. That was nice. How about that? All right, so now we can solve for QP, and that equals NC, which was 9, times AP, which was 1200, and C, which was 3.14. So I get an answer here of 33912, or approximately 34 kips. Now, I'm putting approximate numbers here, but you probably would keep it in that on the real exam. So then your Q total is equal to, just add them up, right? So we had about 33.9 kips plus 150.7 kips, and that equals 184.6 kips. Check my math. All right, looks good.
Yep, looks good. That's a nice pile too. If you get 184 kips out of your pile, you're doing pretty good.
That's a good one, huh?
Yeah, when we drive pile, we're usually in the 30-foot kind of depths just because of soil conditions. And we're usually just north of 100 kips per pile. So 184 is a nice pile.
That's a solid one.
It's solid.
So this was a quick example of a deep foundation. Like I mentioned earlier, there's a lot of different things they could test you on, and it's a whole nother live that we probably could do problems on dedicated to that. So, but regarding this particular problem, any questions you guys have watching this, and if you have any, feel free to email us too. If you're watching a replay of anything. We'll also be putting this on the course eventually. Kevin asked a question. If the question did not say varies linearly, then C in Q's equations would have been 1200, assuming the soil profile was all the same, correct? I would assume so, Kevin. Yes. If they did not say that, if they did not say varies linearly in the problem, yeah. This is one of those things where you got to pay attention to some of that wording in the problem. Good catch. Never seen an example that says varies linearly, so all good to see. Yeah, that's to throw you off, Kevin. Make you think a little bit more when you're solving these PE problems. Okay, if you have any more questions, let us know in the comments. I'll come back to it. Let's get to these last few that I have, and then we'll let you guys get back to your weekend. All right, problem number 6. This is a theory question, deep foundation theory. Most problems I specifically remember were more theory geared on the exam dealing with these. So, all right, many deep foundation theory problems can pop up on the exam. Here's problem number 6 that we've got for you. Which of the following is true for the use of cross-hole sonic logging used for quality control for deep foundations? How many of you out there have heard of cross-hole sonic logging? I don't know if many people have, but this basically falls under dynamic pile testing. It's actually a non-destructive test for quality control, is what this is. Sorry.
Yeah, and it's typically used on big caissons. So when we do big bridge work, and we've got big piers that we're constructing, this is how they test, I guess, whether the concrete has got a nice uniform consistency across the.
Michael's heard of them, and to be honest with you, I use these all the time when I do project management now. But in the transmission world, if we hit groundwater and we could not get, if it was considered a wet, hole, then we would use cross-hole sonic logging to test the installation of their work and see if there was anything wrong with that foundation at specific levels of that foundation, because you want your foundation to be solid, and there's a specific point on that foundation where it sees the maximum loading on it. And if you have problems at that spot, then you've probably got problems. So.
Yeah, you just don't want big honeycombs, big voids in your concrete matrix.
Blowouts with soil coming into it.
Exactly.
So, okay, let's look at this. Which of the following is true for the use of cross-hole sonic logging used for quality control for deep foundations? And you're thinking in your head when you look at this, do I even know what cross-hole sonic logging is? Like, I've played Sonic the Hedgehog, but I have no idea what this is talking about, and maybe that's you. But you need to read up on it. So, A, CSL is not sensitive to the surrounding soils or pile length. B, it can be used to find defects and determines where the defects are located. C, it cannot find diameter changes or bulges. And D, all the above. So these things can do quite a bit. Definitely, CSL is not sensitive to the surrounding soils or pile length. It can be used to find... I know it can be used to find like soft bottoms if the tubes extend to the bottom of the shaft, if you go that deep. It can find multiple defects and determines it can determine like a quadrant where those defects are located. It really, it cannot find diameter changes or bulges. It's like a pulse of energy, which is probably the one that's going to throw you off. And it cannot see outside the cage and does not detect centering or covering a problem. So I'm reading some other things about cross-hole sonic logging that maybe you don't know. So yeah, the answer I'm going to go with here on this guy is D. So yeah, these are the kinds of questions you're going to see on the exam typically if you're going to get a theory type question. But that's the answer for cross-hole sonic logging, D.
Yeah, pretty straightforward. You just got to understand your CSL.
So, like I said, to try to wrap this up and keep you guys here for an hour, get a good textbook, get a good geotech textbook that you can dive into some of this material if you haven't already. I mean, we're sitting in April already, so the exam's coming up. I mean, hopefully you've got something going already, but for future test takers, make sure you do have a good textbook. Like I mentioned before, Goswami's review manual does dive into some seismic material and this material where the CERM doesn't necessarily hit it as hard. But I think between a good textbook and that, you should probably be okay on the exam. But if anybody else has any other resources, we are game to hear them. Another good resource is just generally studying some seismic material in general. And I know many people in California do have to take the seismic exam, and there's some good resources built for that exam that could be applicable to this particular depth exam. So, Mark, any last thoughts before we wrap this up for the day?
No, man, I think you nailed it. I think you did a great job here.
Okay.
I'm seeing a lot of questions, so that means everybody understood exactly what you did.
Good. I hope so. Like I said, guys, if you guys need help with anything with the PE exam, don't hesitate to email us. We are around. You can reach Mark at civilengineeringacademy.com. I'm Isaac at civilengineeringacademy.com. That's ISAAC. If you do need a course, whether that's FE, PE, or specifically to your depth, our course for the depth section includes all material, so you're going to get it all, even though you might not want it all, but that's pretty sweet. And you can go check it all out at civilengineeringacademy.com, and that's going to probably wrap it up for us.
Yeah.
All right, guys.
It's going to be it. Thanks for letting me join in, Isaac. It was fun.
No problem. Everybody have a good weekend, and we'll see you on the next live workshop. See ya.